Today, we're going to follow the unseen journey of water. I mean, think about it. A trip that starts in some far-off river or reservoir and ends up right at the root of a plant. It's all thanks to the incredible and maybe a little underappreciated field of irrigation engineering. I mean, it's a question we probably don't ask ourselves very often, right? You see these huge green fields in places that are, well, pretty dry, and you just kind of accept it. But behind what looks like magic, there's this massive, carefully calculated system, an engineering marvel, really, designed to get the perfect amount of water at just the right time across these enormous distances. So let's trace that journey, step by step.
Okay, so our journey kicks off with a really fundamental challenge. You've got to get water from where it is to where it's needed for farming. And look, we're not just talking about digging a ditch here. This is about sustaining entire civilizations. So what is irrigation engineering, really? At its heart, it's the science of managing water to grow food. It's this cool blend of two fields. You've got hydrology, which is all about understanding how water behaves out in the wild, and then you mix that with fluid mechanics, the physics of how water moves through pipes and canals. And the whole point? It all comes down to one simple, crucial goal: growing crops.
All right, before a single drop of water even starts to move, the engineers have to pull out their calculators. They've got to figure out exactly how much water a certain crop needs to be healthy and productive. You can think of it like they're placing a super precise bulk water order for millions and millions of plants. The first piece of that puzzle is something called delta. Now, here's a good way to think about it. Imagine you could capture every single drop of water a wheat plant needs for its entire life. Now, if you poured that water over the small patch of ground it grows on, the depth of that water, well, that's the delta. It's basically the crop's total water budget for the whole season. Now, the other side of that coin is a concept called duty. So, what's duty? Well, it's all about measuring how efficient your water supply is. It basically asks the question, if I have a steady stream of water, let's say 1 cubic meter per second, how much land, how many hectares can I actually irrigate with that? So, a high duty means you're being super efficient with your water. You're getting a lot of bang for your buck, so to speak. And here, this is where it all clicks into place. This little formula is pretty much the golden rule of irrigation planning. It's what connects the crop's total water demand, that's our delta, with the efficiency of the water supply, our duty, all tied together by the length of the growing season, B. With this one equation, engineers can plan out the entire system. We're talking everything from how big the main reservoir needs to be, right down to the size of the smallest little channel. But wait, the precision here goes even deeper. It's not just one number. See, engineers build it up in layers. They start with the consumptive requirement. Think of this as the bare minimum the plant needs to drink just to survive and grow. But that's not enough. On top of that, they add water for the net requirement, which is extra water needed to wash harmful salts out of the soil. And then finally, they calculate the field requirement, which adds even more water to make up for what's going to be lost when you actually apply it to the field. It's this multi-layer calculation to figure out the true amount of water you need to send down the line.
Okay, so once the math is done and they know exactly how much water is needed, the next challenge is, well, it's epic. It's building the infrastructure to actually move it. We're talking about creating these massive man-made rivers, canals, that act like highways for water.
Now, the key thing to understand is that you can't just dig a big trench and call it a day. It's a real balancing act. If the water flows too slowly, all the silt and sediment in it will just settle at the bottom and clog the whole thing up. But if it flows too fast, it'll start to erode the banks and the bed of the canal, basically tearing it apart from the inside. The goal is to find that perfect, just right speed for a stable channel. And for more than 100 years, engineers have basically used two major theories to find that balance. First, you had Kennedy's theory. This was the original, based on just going out and looking at canals that were already working well. Later on came Lacey's theory, which was a bit more comprehensive. It wasn't just about observing, it actually provided a whole set of equations to help you design the ideal, stable channel right from the start. So, we've done the math, we've built the water highways. But now we get to what might be the most critical part of the whole journey, the last mile. This is all about getting that water from the canal to the actual plant roots. And the name of the game here is doing it with as little waste as humanly possible. And how do you measure success at the stage? Well, it's a metric called water application efficiency. And it's a simple but kind of brutal ratio. For all the water you deliver to a field, what percentage of it actually gets stored in the root zone where the plant can drink it up? It's that simple. If you deliver 100 liters and only 70 of them get to where they need to go, your efficiency is 70%. So, what happens to that other 30%? Where does it go? Well, some of it just runs right off the surface of the field, and another chunk sinks too deep, way past the roots, in a process called deep percolation. And trying to shrink those numbers to minimize that waste, that is a huge, huge challenge for engineers.
And this is why all of this matters so much. Every single drop that's lost is a direct hit to our food production. It's a waste of our most precious resource. Improving that efficiency, even by just a few percentage points, can have a truly gigantic impact, not just locally, but on a global scale. Now, to manage this whole journey from start to finish, engineers also have to build structures to control the incredible power of water. We're moving away from the calculations and into the world of concrete and steel, the world of taming nature. Just look at the OG spillway. You've probably seen this elegant S-curve on the top of big dams. It's beautiful, but it is absolutely not just for looks. That specific shape is engineered to guide huge volumes of floodwater smoothly over the top, which stops the water from becoming this turbulent, destructive force that could literally rip the foundation out from under the dam. It's like a giant, perfectly designed safety valve. But the biggest threats aren't always the ones you can see. Water is, well, it's relentless. It doesn't just push against a dam. It's always trying to sneak underneath it. And the slow, hidden seepage can just gradually wash away tiny bits of the foundation, year after year, weakening the whole structure from below until, boom, catastrophic failure. The solution to this is it's so clever. It's called Bly's creep theory. And the idea is you don't even try to stop the water completely. Instead, you make its journey as long and as difficult as you possibly can. Engineers build these underground barriers that force the water to take this really long, winding path, like an obstacle course. And over that long creep length, the water just loses all its pressure, all its energy, so by the time it gets to the other side, it's completely harmless. So, from calculating a single plant's thirst to building canals that span continents to taming the power of floods, irrigation engineering is without a doubt a monumental human achievement. The principles we've touched on today are the foundation. But the big question, especially as our climate changes, has to be, how do we get even smarter? How do we build on all this to truly make every single drop count?